So, welcome to Math 202, which is an introductory course in calculus. So, naturally, we're going to start with Chapter 1, which consists of a handful of review topics that I've chosen because they're particularly important for this course. Now, all this material that we cover in Chapter 1, there's 4 sections in total, should be review to you. But let's be totally honest, the summer has gone by, right? You've had plenty of time to think about other things, and it may be some time now since you have seen these ideas, had a chance to practice with them, or even thought about them at all. So that's the purpose of this section, is to give you an opportunity to refresh yourselves and bring those ideas back to the forefront of your brain. So the first section, 1.1, is all about the mathematician's favorite object, called the function. Right? So almost every problem we deal with in calculus will involve functions in some way. So it's absolutely crucial to have a clear understanding of what they are and how they work. So that's what we'll jump into right now. Okay, so the first thing we're going to talk about is what is a function, right? And you can see I've left a little blank space here to fill in. This, by the way, this DEF with an N afterwards, underlined twice, that's just an abbreviation for definition. If you ever see that, you'll see that plenty in this course. But wherever you see this just means I'm about to define something new. So there's a little space here, so we'll fill in the blanks. This is actually the definition of a function. So we can fill that in now. And actually, before we go through these two lines carefully, I actually want to draw a picture of what a function is, because I think it's really helpful to think about a function this way. So roughly speaking, what is a function? A function is just something that takes real numbers as input, and gives you back real numbers as output. Okay, so you can imagine a function like a machine that looks something like the following. I always like to draw this diagram at the beginning of a term. So let's say we've got a function f. Okay, so it's named. Usually we name functions with a letter. In this case, we're using the letter f. So you can put something into the function as input. So let's say quite often you'll use the letter x to represent an input value, but you don't have to. You can use any letter you like, but I'll just use x this time because that's standard. And then you're going to get something out of the function. You'll get back something as output. And that's what this notation f of x means. Okay, so f is the function. You could take some value, which I've labeled as x, as input. You can plug it into the function, and then maybe the gears spin, it makes some noise. Something's going on inside the function. You don't necessarily need to know what, but all you know is that something is going to come out, and that's what this notation represents. This represents the output from the function f when you plug in the value x. Okay, so I just want to add a little bit more to this. So this x is our input value. And f of x over here is the output value. So this diagram is quite simple, but it's a really nice way to think about functions, and this is the picture you should have in your mind whenever you're trying to think about what a function is or how it behaves. So from one function to another, what differs? What happens inside, right? And how the input value determines the output value. And that's going to depend on what the function is, right? So different functions will do different things. Okay, so let's go back up to this definition and read it carefully now. So a function f on a set D, and this set D, I want to pause for a moment, this set D is going to end up being called the domain of the function. So this set D, really, in your mind, you should be thinking about this set D is just the set of all things that are allowed to play the role of this variable x, the set of all things you're allowed to plug into the function over on this side. Okay, so a function f on a set D is a rule which assigns to each element x in D. I'm going to come back to this in just a moment. This just means x is an element of the set D, or x is inside D, or x belongs to D. We'll write that down momentarily, but let's finish this definition. So a function f on a set D is a rule which assigns to each element x in the set D a real number f of x. So this x, this is the input value that you're plugging in over here, right? And the real number f of x that the function assigns to it is the output value. Okay, and then in this case, like I said, this set D, it has a name. It's called the domain of the function. So let's fill that in here. In this case, D is called the domain of f. Okay, so, and then just a reminder, this notation just means x is an element of D. Or you could say x belongs to D, or x is in D. Any of those things, any of those ways are fine. Really, D is a set. It's got some objects inside of it. This statement here just says that x happens to be one of them. Okay, so the domain is the set of all possible input values that you can plug into the function. What about the set of all possible output values that might show up as output values, like that the function might spit out afterwards? Well, that has a name too. The set of all output values is called the range. So that's what we're going to say here. So the range of the function f is the set, and here's the definition of the range. Now, let's take a moment to read this carefully. How do you read something like this, right? May have been a while since you've seen something in this form, but this is called set builder notation. It's a way of describing a set using a very specific language. So here's how you would read this out loud. This open curly bracket, you would read this as the set of all things of this form such that this criterion here is true. So it's the set of all things of the form f of x such that x happens to be in D, right? Remember, D was the domain of the function f. So really what this is saying is take all the elements of the domain, plug them all into the function f, record all the output values that happen, and put those together in the set, and that's what this is. Okay, so this is giving you a typical form of an element of the set, means it has to appear as a possible output value from f, where you plugged in some x, where, by the way, x would have had to have been in the domain. And of course, that needs to be true for this to make sense. So this is called, let me remind you that this is called set builder notation. We'll use that fairly frequently in this course. If you haven't seen that in quite some time, don't worry, you'll get plenty of chances to be reminded on how it works. Okay, but I just want to remind you of what it's actually called. Okay, so that's just basically the fundamental idea of what a function is, right? You've got a domain and a range, and this is how you should think about functions. Okay, some notation just to make your life easier. The first one is if you want to write down the domain of a function, you can just abbreviate it with DOM. So DOM of f, this just means the domain of the function f. And then the second piece of notation, there's just a similar thing you can do for the range. If you want to write down the range, you can go RAN of f is the range of f. So you can see this is a lot easier to write than this phrase here, right? So it's just gives you a way to make things more brief. Okay, so now the domain D in this definition will not necessarily be specified. Sometimes it will be specified, and that makes it easy to identify the domain. If you're told what it is, then you know what it is. But if you're not told what the domain is, then it is automatically taken to be the maximal possible set of permissibility, right? It's the biggest set you could possibly have as the domain. It's the set of all input values that would possibly make sense for the function. So for example, down here, we're given a function, so define f on r. By the way, what is this symbol r? Let me remind you what that means. So pardon me for interrupting myself a bit here. So r, this is the set of all real numbers. So that's a very important set for this course. It's the set of all numbers that we will ever work with in this course. Okay, so the picture is the number line. Okay, so if I draw this horizontal line, arrows on both ends, I can put 0 anywhere I like, really, but let me just put 0 here. I've got 0, 1, 2, 3, right? I got all the whole numbers. I've got 0. I've also got negative numbers. I've also got fractions. I'm going to sneak a fraction in here. Right between 0 and 1 is, I'll put it up here, 1/2. Right? And I can even put down irrational numbers, like right between 1 and 2, somewhere roughly around 1.4, you have the square root of 2. What else do you have? Roughly around 3.14, a number just bigger than 3, you have the irrational number pi. That's also a real number, so maybe I'll label it R for the real numbers. This is called a blackboard R, by the way. It's a capital R where you've got 2 lines on the left-hand side. So basically any number you can think of. And if you've ever talked about imaginary or complex numbers, forget about those. They're not real numbers. They won't be part of this set. But any number you can write down, whether it's a whole number, 0, negative, rational, irrational, they're all included in the real numbers. So this is called the number line. Sometimes it's useful to draw this line to get a picture of something that's going on. Okay, so let me go back here. So define f on R by f of x is equal to x squared plus 3. Now, this time, looks like the domain was specified here as R, right? And of course, this is allowed, right? Because this ought to make sense, this rule here. How does the function work? You take an input value x, and then you output the value over here. So you take your input value, you square it, and you add 3. Now, does that rule make sense for every input value in the reals? Sure, you could square absolutely any number you like, and no matter what the result is, you can always add 3. There's no concern about it not being defined. So that's sensible. So for part A, what is the domain of f? It's the set of all real numbers. And in fact, we're told that right here. So for part A, we can use this notation up here. We can write the domain of f is equal to all real numbers. That's just the easiest way to say it. Okay, so for part B, we're going to evaluate the function at several input values. So f of 0, f of 1, f of pi, and f of negative 1. So let's do that. Just a reminder on what that notation means. So if I go f of 0, what do I mean? I mean take the value 0 and plug it into the function up here, right? So f of 0 is going to be 0 squared plus 3, which of course just works out to 3, right? So that's f of 0. It's going to be 3. Let's do the other 3. So f of 1 will be 1 squared plus 3, right? Just take the number 1 and plug it in here. You get 1 squared plus 3. So 1 squared plus 3 works out to 4. And what about the third one, f of pi? We're plugging the irrational number pi into this function. So f of pi, what do? The exact same thing you did for the other two numbers, right? So f of pi, we're going to take pi and plug it in for x, and you're going to get pi squared plus 3. Now, you can't really go any further there, because what's pi squared? Well, pi is already an irrational number, so pi squared is probably going to be an irrational number too. If you add it to 3, it's going to be some number that's difficult to wrap your head around unless you punch it into a calculator. But I don't want you to do that. I don't want you to punch it into a calculator. This is an exact value. As soon as you punch it into your calculator and round it off, it's going to be an approximation. Okay, so that's going to be pretty much a rule in this course. Whenever you are dealing with a number that has an irrational or an answer that has an irrational component, simplify it as much as you can, but then just leave it. So this is completely fine. Pi squared plus 3, that is the exact output value from the function f when you plug in pi. So we'll just leave it like that. Then the last one, negative 1, f of negative 1 equals negative 1 squared plus 3. So negative 1 squared, remember if you square a negative, then the result is going to be positive. So negative 1 squared is going to be positive 1. If you add that to 3, you're going to get 4. So great, that's part B. So that's just a reminder on how to plug numbers into functions. And the last part here, part C, what is the range of f? Now, the range is not so obvious as the domain in this case. The domain was just given to us right here. We were told that f was defined on the set of all real numbers by this rule over here. But what about the range? You have to put your thinking cap on a bit and actually give it some thought here. So, well, what types of numbers could appear as output values from this rule, right? Remember, the function takes an input value and it squares it and adds 3. So, well, which numbers can you get? Here's the way to think about it. Start by looking at the fact that the rule that defines the function f has an x squared in it. Let's start with that. What do you know about the square of something? Well, we actually just kind of alluded to it over here when we were working this out, but the square of something is always going to be positive, or at the very least, it's not going to be negative, right? Actually, it's not true to say that a square is always positive, because it could be 0. If you square 0, you're going to get 0, which is not actually a positive number. But it is true to say that the square of something is always going to be non-negative. So in other words, we can say this: since x squared is always greater than or equal to 0, right? That's what it means to be non-negative. It's either positive or 0. We also have x squared plus 3 is going to be greater than or equal to 3, right? Because if x squared is at least 0, then x squared plus 3 is at least 3. And that's going to be true for any real number x. So for any x in the reals, that's how I will say that. Okay, so what that tells you is that the output value, x squared plus 3, is always going to be at least 3. It's going to be greater than or equal to 3, no matter what the input value is. Okay, so that's how we get our range. So we can say that the range of f is equal to this interval. Okay, it's equal to the interval consisting of all numbers that are greater than or equal to 3. Now I'm going to talk a little bit more in a moment just about how to use this notation, but for now I'll just remind you what this particular interval represents, right? So if I were to draw a picture, and this is where the number line is helpful, you can express this visually like so, right? I can draw the number line, and I can say, okay, here's the number 3, and if I write down this interval here, oops, I better slide this up a bit. If I write down this interval here, what I'm really talking about is I'm talking about I want to include 3. That's actually this square bracket is what indicates that I want to actually include 3. And then this infinity symbol, this means just go forever in this direction and keep including all those points. So I'll just shade all these points. Okay, and that is the range. So this is how I would express the range in interval notation, and this is how I could express the range with a picture, or in graph. Some people might call it graphical notation, and either one is totally fine. I don't have to do both of these, but this is enough. And there's a third way I could actually write down the range using set builder notation as well, but I won't do that here. I'll do that in one of the other examples later, just to remind you how to do that. Okay, so that's the end of that example, and we'll go on to the next page in the next clip.